Alright guys, so this section is actually a little bit odd. I don't want you to get too caught up in it because it really is not much on the AP at all, and it's using a lot of concepts from Algebra 2. The other thing I realized, I'm not the happiest about my notes packet, so I'm going to add some problems at the end for examples. I want to start off with the beginning, which just gives you some sentences. It says, the number of bighorn sheep the number of bighorn sheep in a population increases at a rate that is proportional to the number of sheep present. So, what that means is the amount that's there directly affects the rate at which the population increases. I want to kind of talk about the word proportional. Let's start with that, because if you remember from other math classes, let's say that you say the statement, the area of a circle is directly proportional to the radius squared. When you say the word directly proportional, that's why there's a constant. Now, you guys know the area of a circle is pi r squared, so the constant is equal to pi. But that's what the statement proportional means. If you are directly proportional, so if y is directly proportional to x, that would be the equation that you're looking at. So we're going to take what I just mentioned and look back at the statement. So, the number of bighorn sheep, so let's say sheep is S, in a population increases at a rate that is proportional to the number of sheep present. So, over here, the rate. So let's talk about rate. Well, rate, when we're talking about real life, I'm going to talk about time. The fact that the population is with respect to time. The proportion is directly related to the amount of sheep that are there. So, that would be the differential equation that I would be solving. So I'm going to go back and look at just the general statement. If the rate of change is proportional to the amount present, then the change can be modeled by, and in this case, the change, I'm going to write it underneath because that box is a little small for me. The amount of what you have, let's call that y. With respect to time, because now we're doing real life situations, we talk about rate of change in terms of time, is equal to the amount present, or proportional to the amount present. So this is the proportion constant, and this y, which I'll box in blue, is the amount present. Okay? So why is that so important? I'm going to continue on this page, but I'm going to insert a little bit of room. So let's take a look at that. And dy over dt is equal to k times y. So why would that be so important? Let's take a look. So I'm going to solve the differential equation. Left side, pretty easy now. Hopefully you guys know that y to the negative 1 would be the ln of y. The right side would be k squared over 2 and then plus, oh wow, made the mistake that I told you guys never to do. The variable is t. So, in this case, if the variable is t, then that is the antiderivative of k. So just in case you're a little confused, it's kind of like taking the antiderivative of 2. It would be 2x. The 2 is represented by the k, okay, constant. Alright, so I'm going to solve for y. So take e to the, and we get that the absolute value of y is equal to e to the kt, and I'm going to change this to multiply by e to the c power. To isolate the y, I'm going to need a plus or minus, and I'm going to move the e to the c into the front. I'm going to move e to the kt to the back. I'm going to replace this nice little constant with an a, which should look very familiar. So what we've just done is kind of proven the equation for compounding continuously. The relationship has to do with the fact that the rate of change is directly proportional to the amount that's there. So if you look at the two equations, they're very similar. So in this chapter, or in this section I should say, it's going to be really tempting to just use the memorized formula. But I'd actually like you not to. I want you to start every problem with the differential equation. This being the differential equation. So in your homework, I am going to look for the fact that your differential equation is the start. If you start here, I will mark that incorrect. I want you to actually deal with the differential equation. And that's purposely because I want you to get a little more practice with that. So, the exponential change, you really want to deal with the fact that we're starting off with this equation. And yes, in the end, you do end up with this equation. That is going to be very helpful for us. All right? So, I have here a few formulas because I believe that there's at least one problem or two that I gave you with Newton's law of cooling. Just so you understand, this T sub S right here is the surrounding air temperature, meaning if you take something out of the oven, the T sub S would be the room temperature. All right? The problems that you have, if you're using Newton's law of cooling, you'll start with the formula given right there. In terms of radioactive decay, the amount of radioactive element left after time is given. So sometimes they give you the formula, which is nice, and that does look exactly like the PERT formula, except for you have a negative KT. We're going to talk a little bit about half-life. So what I want you to notice is that when you deal with half-life or even doubling, something that you want to double, in terms of that, we don't have to worry about how much you actually have. So I want to talk about that. So it's saying, well, a half-life would be when you have half of what you started with. Now here's the starting amount. So I don't know if you realize, but that constant A is your starting amount. Now if I end up with half of that after some time, now here's what that looks like. And let's say I want to solve. And let's say that we want to solve for how much time it'll take for the half-life. Well, on the right side, I would want to isolate this t for time, so I'm going to take the ln of both sides. And we end up with the ln of 1 divided by 2 is the same thing as ln of 1 minus the ln of 2 equals negative kt. Now let's come over here. Ln of 1 is the same as 0. So we get negative ln of 2 is equal to negative kt divide by negative k, and we end up with ln of 2 over k is equal to t. What I want you to notice is we didn't know anything. We knew that you have something with a half-life, and you have the half-life formula sitting there. So what I want you to notice is it doesn't matter how much material you start with, so how many grams or how many particles you start with, your half-life completely depends upon your constant k. That's what you need to know to figure out a half-life. So the process that I went through here is actually what I want you to do, because guaranteed no one ever remembers the half-life formula, but you do remember how to solve. So I am going to show you through a few problems that I don't actually just memorize that t equals ln of 2 divided by k. Alright, so let's kind of start off with some problems that you have in the book. If you want to grab your book and put it next to you so that you can look at them and not have to write down each problem, you may. Just press pause. So let's start with, let's look at, it says find the solution where you're starting out with this. And let's do number 14. So, you're going to start off with, yes, I want you to go through this process, and yes, we know that what the answer is going to be, but I still want you to do it. So that becomes the ln of y equals kt plus c. We're going to take e, both sides. We get absolute value of y is equal to e to the kt times e to the c. We end up with y is equal to plus or minus e to the c times e to the kt. We're going to replace this with a big old A, e to the kt. So I want you to go through the process. Then we're going to use the 2 points given. So they say at time equal to 0, y is 60. So that helps you find A. So that's what I have so far. And then the other value that you're getting, 30, is equal to 60 e to the k times 10. And then here we're going to actually have to solve. And I'm going to move that over to next page so I have enough room. Alright, so paste. So I want to solve for k, and I would do that by taking the ln of both sides of the equation. Ln here. Actually, before I do that, I didn't realize that the e is not by itself, so I'm going to divide by 2 first. Oh, divide by 60, which makes 1/2, I'm sorry. And then now that the e is isolated, I want to take the ln of both sides. Now, I couldn't do it in this line right here because the 60 was in the way. You have to isolate the e for this to actually work. So we get that the ln of 1/2 is equal to 10k. Now, if you remember from before, the ln of 1/2 is the same as ln of 1 minus ln of 2. Using a expanding rule, this is 0. I get negative ln of 2 is equal to 10k, and k is equal to negative ln of 2, all divided by 10. I believe that's what they asked for. Find the constant k. Alright, so I actually do this problem to kind of show you, number one, how to solve the differential equation, and secondly, how to solve for a and k given 2 points. If they don't give you the initial value, it does make the problem slightly harder, but you end up solving a system of equations. Alright, half-life. So I wanted to go through this half-life problem. So we have the differential equation. Negative k times y. Where t is measured in minutes, what is the decay constant k? So, we know in the end that the half-life is 65 minutes. So, here we go. We're going to start by isolating the y on the left side. We're going to keep the negative k multiplied by dt. We're going to integrate, and look at where I put the integral symbol, right there. Ln of y is equal to, bring down your negative, and then k times t plus c. I'm then going to take e, both sides, and we get absolute value of y is equal to e to the negative kt, and watch what I do, multiply by e to the c. The absolute value we're going to get rid of by using the plus or minus, e to the c, multiplied by e to the negative kt. Alright, this will turn into a big old A, and then e to the negative kt. It says that we want to find the constant k. We know that the half-life is 65 minutes. So if I'm going to have half the amount left, then I know that this A was the original amount. Well, half of it is how much I have after 65 minutes. The A's will cancel. I get 1/2 is equal to e to the negative 65k. I'm going to take the ln of both sides to cancel this e. I get that the ln of 1 minus the ln of 2 is equal to negative 65k. And then I get negative ln of 2 divided by negative 65 is equal to k. And therefore my constant is ln of 2 divided by 65. I know it does seem really redundant to do that process over and over again. It also seems redundant because you had the formula to find k or to find t. Originally, based off of one of the examples I did, but no one actually ever remembers that formula. Okay, so number 24. Let's see. So this is more similar to the type of problems that you get when you see an AP problem. it almost looks like an Algebra 2 problem. You can probably find this exact problem in an Algebra 2 book. So I'm going to kind of walk through what this would look like. It would be multiple choice, and it would start exactly the same way. And this is the key. Increases exponentially with time. That in itself tells you that this is not the exact problem I wanted to go through. I was hoping they said that the population, the rate of change of the population is proportional to the amount present, is what I was hoping for. So I'm going to go through the whole process of using the differential equation to start off. Instead of starting with the exponential equation that we're going to end up with anyway. So to start off, I'm going to go through this process one more time with you. ln of absolute value of y is equal to k t plus c e. Absolute value of y is equal to e to the c times e to the kt plus or minus. I'm going to put that there and turn that into a e to the kt. Alright, then I'm going to use the 2 points to kind of show you how to find the equation given 2 unknowns but 2 points. Alright, so we know that at the end of 3 hours there are 10,000. And then we also know that at the end of 5 hours there's 40,000. So, actually I shouldn't have made that line all too extra big there. So, really you could do the problem by solving for a on both sides. And I'm going to do the same thing over here. And then because they're both solved for a, we can set them equal to each other. In a sense, I'm going to cross multiply. I'm going to do myself a favor and kind of save some steps. I'm going to multiply this e to the 5k to the left side, and I'm going to divide by 10,000 on the right side. So I end up with e to the 5k divided by e to the 3k equals 4,000, or 40,000, sorry, divided by 10,000. Then I end up with, alright, so we end up with, in terms of how you do this, you would subtract powers when you have a fraction with the same base. So you end up with e to the 2k is equal to 4. And to solve that, you would take the ln of both sides. And you get 2k is equal to the ln of 4. Therefore, k is equal to ln of 4 divided by the whole thing divided by 2. And let me write out the answer one more time just so you're very clear on what it looks like. K is equal to the ln of 4 and the whole thing is divided by 2. Okay? So, it asked me how much bacteria was initially present. So this gives us the constant that we're going to need. Let's see if I can squeeze in my work right in the middle right here. Oopsie. Alright, and I'll do that in black so it kind of shows. To find my a value, I would then have to, and what I'll do is go to another page because I don't have enough space. Let's see. So I'm going to use one of the equations that I solved for a. Doesn't matter which one you choose because they both are equal to the a value. And if you remember, the a value is our amount initially present. We found that k is equal to ln of 4 all over 2. So I end up with 10,000 divided by e to the 3 times k, ln of 4 divided by 2 equals a. To be very honest, you're going to end up being permitted to use a calculator for this. But we can do it without. I'm going to rewrite that power as 3 halves times ln of 4 equals a. And I still have the 10,000 in the numerator. And I'm going to rewrite that as ln of 4 to the 3 halves. Why would I do that? Because when you do that, it gives you the ln and the e right next to each other, which means that they're going to be able to cancel. There are many other reasons as to why, but that's my little way of making sure I do that correctly. And then 4 to the 3 halves is all you have left on this side. Therefore, you get 4, square root of 4 is 2, 2 to the third is 8, and you get 10,000 divided by 8 equals A. Divide that by, I guess, 4. Alright, divide that, I think that's divisible by 8, 1250. Alright, that is your A value. That is how much was present. Man, that was a long problem. But it went through a lot of good things. It went through a lot of rules about ln and log, or ln and exponentials in general. It went over some rules about powers. You looked at how to solve. A lot of things that are very important. So if you didn't get through this problem, or you feel like I might have skipped a step here and there, I would work through it. Kind of press pause, do it the way that you wanted to, and see if you end up with the same answer. Alright, moving on. Do I have another one? I do. So I only showed you this problem because this is essentially the same exact problem we just did a second ago. It's a little bit easier because they gave you the y-intercept, but any problem where they give you how much you have at a certain time. So in this case, these would be the points. But the problem that we just did a second ago, it said, you know, at time equal to 3 there was 10,000, and time equal to 5 there were 40,000. Every single one of those problems is going to be done the same if the rate of change is proportional to the amount present. Meaning, if they are exponentially related. Alright, and therefore, I gave this last one to kind of show you that process. I'm not going to do it, but I wanted to show you it's exactly the same. The process of raw sugar has an inversion step that changes the sugar's molecular structure. Once the process has begun, the rate of change, so here it is. Let's say sugar, so S. Of the amount of sugar is proportional to the amount of raw sugar remaining. If 1,000 kilograms of raw sugar reduces to 800 kilograms of raw sugar during the first 10 hours, how much will remain after another 14 hours? So at time equal to 0, we can say that there was 1,000. And at time equal to 10, we can say that there's 800. And the time that they want you to solve for is another 14 hours, so that would be 24. So this is kind of the breakdown. You would end up using the differential equation to solve for the formula S. If it confuses you to use an S, you can always use the Y, just like we did a second ago. Okay? And from there, you would substitute in the 2 points. What's nice is they actually gave you the A value sitting right here. You would use the other point to solve for K, and then substitute in your time. So I just wanted to walk through the fact that each of these problems can be done by starting out with the exponential equation of y equals a e to the kt. I very, very specifically do not want you to start there. I want you to start with the differential equation. You should end up with the same exponential equation when you're done for each problem. So hopefully the homework won't be too bad. Inside of your homework packet, I believe there should be some multiple choice somewhere to be found on this section also. And I put in this example for Newton's law of cooling in case you needed it. I'm going to go back and steal the equation that we have here. So it looks kind of similar in a sense to what you've been doing. Paste that guy. Right? So in case you can't read it, it says the temperature minus the surrounding temperature is equal to the initial temperature minus the surrounding temperature times E to the negative K times T. So just so you understand what these all are, this is the final temperature after however amount of time you're talking about. This is the surrounding temperature. This is the initial temperature. and K is your constant. So that should help you. I believe I gave you at least one problem to do with Newton's law of cooling. And that's it.